This is sum over integer squared and can be calculated with this formula. But how do you know that it holds true? And how did I come up with that? The topic for today is to answer these questions, but also taking it a bit further than some special cases. At the end of the video, you will not only know how to derive the formula for sum of squares, but something more general. Okay, let's try some values to get the feeling of why this formula makes sense. If we try n equals to 0, then we get 0 squared on the left side and 0 on the right side. Good. If n equals to 1, we get 1 squared on the left and the sum of the fractions to the right. Seems legit. And the trend looks like it will continue. For now, we know that at least the first 4 cases where the sum is defined agrees with our formula. Now, you might be tempted to also show that it works for a case when n equals to 4. And this is exactly what we will do, but we will rephrase it so it applies more generally. So instead of specifically checking that n equals to 4 works, let's check for all n plus 1 cases. The reason why is once the scenario n plus 1 equals to 4 is shown to be true, that becomes the new n, and then the new n plus 1 will be checked. This process repeats on its own until all the cases have been checked. To put it in perspective, this is what needs to be true in order to get all the n plus 1 cases checked. But notice that these parts are actually the same. So by substitution, we get the following equation. Recall which assumptions were made so far. Our formula works for any integer n, and if we add the next term n plus 1 squared, then the formula must successfully predict the next value. If we did not make any false assumptions so far, then we expect to get the same stuff on both sides of the equal sign. And you can convince yourself by doing some algebra. This equation indeed holds true for any integer n. Speaking more generally, if we got any function f whose summation formula is s, then the following equation must hold true. Well, with a little caveat. Any formula s of by a constant will satisfy this equation. To make sure we only get one and only one solution, we need to check for a case where the formula successfully predicts the outcome. And that fixes the constant to a unique value. But normally, this is not a big concern. The reason why we came up with our hypothetical formula s in the first place was because it looked suspiciously accurate for the first 4 values. So the checking step was already done. The equation you look at is called the Telescopic Equation, which I like to write it in this form. A simple looking equation, but has a lot of meaning to it, which we will cover in the future. Okay, so it's kind of easy to prove a formula once we are given one. You just plug in the relevant expression into the telescopic equation and see if it holds true. But how in the world do you come up with it? Well, let's do some calculations so we can derive the formula for sum of integers squared. Then try to generalize the idea so we can answer the question in the beginning of the video. Let's say you were trying to sum the positive integers. Geometrically, this corresponds to adding rectangles so they form a triangle-ish shape with width and height n. So the actual value for the sum is approximately the area of the big triangle, which is 1/2 n squared. If we instead sum integers squared, the sum will create a pyramid-ish volume, which is 1/3 n cubed. So I think it's not too big of a stretch to assume that the sum can be expressed in terms of a generalized polynomial of degree 3. Here I assume that the lower order terms will compensate for all those extra volumes created by the corners of the small cubes. Now, you can actually replace the first coefficient with 1/3 if you like, since we already kind of know it from the volume of a pyramid. But writing it in this form will help us to recognize patterns later on. An exercise for you who likes to improve: show that you will always get the polynomial with a degree higher than the polynomial you are summing over. Okay, now we have a suspicious candidate, which we know that it works for some value and hope it will keep working for the following n+1 terms. With this information, we can make use of the telescopic equation derived from earlier. We simply plug in the suspicious formula on the right side and what we are summing over on the left side. What we get is the following. The following algebra steps are basically for solving the coefficient a's. The steps are quite straightforward. I encourage you to pause the video and try it out for yourself. It gives you some intuition on the following content beyond what I can show you in this video. Alright, here we go. This system of equation is what we are interested in, which can also be written in this form. We get to know the coefficients by solving it from top to bottom. We can then plug in these coefficients into our hypothetical formula, and we end up with the explicit formula for sum of squares. Formally, we need to substitute this expression into the telescopic equation and checking a trivial case to make sure that our assumptions are made correctly. But besides that, this is it. Now, if we want to know the formula for sum of cubes, we can assume that the formula takes in the form of a degree 4 polynomial. Substitute into the telescopic equation, and after a bunch of work, you arrive at some sort of system of equations, which is rather easy to solve. But that's a lot of work to get there, and only gets worse the higher order polynomial you are trying to sum. Fortunately, there's a little trick we can apply, so we can skip most of the algebra and arrive directly at the system of equations. Let's look at the system of equation from last example. Now, let's forget the coefficient a's for a moment and only focus on the numbers. Don't worry about the scary looking matrix if you have never seen it before. You can think it as a clean way of writing down system of equations. But doesn't a coefficient remind you of something? No? Okay, I will fill in some ones and also rotate it. I'm convinced that all of you have seen this pattern before. And the fascinating thing is that not only is the coefficients related to the Pascal's triangle, but also the right side corresponds to a row. Alright, let's try to summarize this amazing pattern. We were trying to solve for the 3 coefficients for a degree 3 polynomial. The right side had 3 numbers. So we looked at the third row of Pascal's triangle and placed them on the right. Now, to calculate the coefficient for a's, you need to skip the diagonal ones and mark the neighbor number from bottom up and fill in the rest with zeros. That forms the coefficients for the first equation. For the second row, you do the same, but now you slice 2 numbers starting at the bottom and end diagonally upwards. Fill in the rest with zeros. And of course, you repeat for the third row, slicing 3 numbers bottom up. Perhaps you can remember this as slicing numbers bottom up. And notice, we actually got a symmetry property, meaning that it doesn't matter which side you choose to start. Just make sure you start at the bottom and end diagonally upwards. A way to remember this is perhaps row of degree shall be on the right, slicing numbers bottom up. Let's look at an example where we sum integers cubed. With the experience of previous examples, we expect that the formula takes in the form of a degree 4 polynomial. What should ring in your head now is row of degree shall be on the right. Okay, we got the degree 4 polynomial, so we look for the fourth row in the Pascal's triangle. The row of numbers shall then be on the right. To get the first row on the left side, we skip the diagonal ones and slice one number bottom up and fill in the rest with zeros. For the second row, we slice two numbers starting at the bottom and end diagonally upwards, followed by 3 and finally 4. After completion, you can convert back to a system of equation format if you like and solve for the coefficients. This is the final answer for this example. Although it's cool to be able to find an exact solution, but sometimes it's just too difficult. Or maybe an explicit form doesn't even exist. It is in these cases where we look for approximate solutions. I will show you a more systematic method to guess the formula, to then come up with good approximations for another class exam. But that is a topic for the next video. I'm looking forward to meet you there.